Hello everyone, my name is Angelos Treklas and I'm from the European Projects Department of Mobile World Capital Barcelona. Today in this video we're going to talk about OPIL, Open Platform for Innovation in Logistics, also known as Logistics Automation Library, a fully automated and customizable library that can serve the needs of the industry, offering efficiency and low-cost solutions.
First, I'm going to give you an introduction talking about the general concept of OPIL library and then its business perspective. Then, we will talk about how OPIL is related with the context of the industrial IoT. Then, we will say a few words about the OPIL architecture and we will have a small, brief talking on its functionality. Let's start with the introduction.
Here you could see a schematic of how OPIL interacts with all equipment and devices of the factory, such as sensors, AGVs, and enterprise applications. Also, its interaction with virtual component simulation software, which is a digital twin of the whole logistics system. From the previous schematic, we can examine another functionality of the library, and we can separate it into two phases. The planning phase, where simulations can be used to design the layout, routes, and schedule routines of the floor plan, and the execution phase, where devices can be connected and any logistic operations can be steered. The Logistic Automation Library can enable, moreover, the continuous adaptation and reconfiguration of the logistics system with low effort and maximum efficiency. So, why should we use the OPIL library? Material handling is a non-value adding activity. There is big uncertainty regarding future demanding requirements and product portfolio. Of course, in a modern factory, they are automated logistics, but they have traditionally low adaptability. In addition, integration cost due to software implementation is always high, as well as system expansion, which is most of the times costly and time-consuming. The OPIL library can adapt easily to new layouts because you can always redesign and optimize routes and speed with precision through simulations. Also, you have adaptation to changing volumes. For example, it is easy to include new AGVs and robots, etc. Or change their production planning and consider even automatic scheduling. Additionally, adaptation to new technologies is possible with a plug-and-play functionality to sensors and ROS-based AGVs. Apart from the production advantages of the platform, there are also economic advantages. Time and installation costs can drastically be reduced as long as the time for system adaptation, and moreover, in the logistics automation library, there are standard interfaces to interact with the factory without any further need for costly extra software. So, what is the OPIL Logistics Automation Library? If we want to conclude to a definition, we can say that the Internet of Things platform that exploits IoT paradigm can enhance communication among the different elements of the shop floor in order to create a flexible and responsive logistics system, either on planning within its simulation phase or its execution phase, as it is seen in the picture. Logistics Automation Library, compared with traditional floor plan, is more centralized. Enterprise software devices, sensors, and routines can communicate with each other. Sensors, for example, can communicate with the central core of the platform with the AGVs, making all the process faster and direct. And now we can talk about the library architecture and its technical tools.
So, on technical tools, we have ROS, Robotic Operation System, which provides libraries specifically developed for robot control, and it can communicate with Fireware Orion Context Broker, that is a data distributed service where every node of the library can write and read messages, and the tool is used by the nodes of the architecture to communicate. So both tools communicate with a software called FireOS, which can establish communication between robots, AGVs, and the main control of the library. The architecture of the logistics automation library consists actually from 3 layers. The lower layer is the Internet of Things nodes, that is the production floor and the ones that perform logistic tasks. Then there is an upper layer, which is the software system layer, which is responsible for logistic functionality and the simulation, and a middle layer, the cyber-physical system layer, which enables communication among different systems. In more detail, the architecture can look like this. In the lower layer, the Internet of Things nodes, you can see robot agent node, responsible communication and messaging of robots, local sensing and perception, which is responsible for mapping and localization, and the sensor agent node, which is responsible for the communication of the sensors. The upper software system layer consists of Task Planner, which consists of Task Supervisor and Motion Task Planning, and is responsible to prioritize the tasks, a module called Business Process Optimization, and the advanced Human-Machine Interaction module, moreover, the Central Sensing and Perception module, which will be examined in detail later. Apart from that, there is an upper and lower layer of the digital twin visual components. Upper layer is the 3D simulation of the floor plan factory, and RAN and SAN virtual components can mimic the corresponding modules inside the digital twin. Here we can see a visual arrangement of the library, formerly known also as OPIL. The heart of OPIL is, as it has been said before, OPIL server, which communicates with all the application modules such as Task Planner, Sensing and Perception, HMI, BPO, and etc. The OPIL server is in control of both the real and the virtual factory, and the whole system is embedded in RAMP, Robotics and Automation Marketplace, where all other tools such as data analytics, graphic representation tools, and other applications are also developed and can be available. Another perspective to examine the logistics automation library is from the view of its functionality. So, concerning functionality of the OPIL library, we can distinguish 2 main functions of it: steer and inform. At the right, you can see clearly what steering is about. Here are the modules that are responsible for the reading and communication of the sensor signals, like the Sensor Agent node, SAN, and the node responsible of the AGVs and the robots to perform operations and follow planned tasks, the Robot Agent node, or RAN, nodes that are running on a local device. In parallel, these 2 nodes exist in the digital twin part as Virtual Components RAN and Virtual Component SAN, with also another module of Virtual Component Actuator, which is a combination of the real sensor signal and simulation. On the left part, we have function modules that determine operations, plans, and tasks, the floor plan, and ensure the smart behavior of the whole structure. These modules are the Task Planner, Sensing and Perception, and the Human-Machine Interaction module, which are running on the OPIL library server and will be examined analytically later on. All modules and the documentation of the OPIL Logistics Automation Library regarding installation files, JSONs, guidelines, and images for the OPIL server can be found in the link that appears on your screen. And with that, we reached to the end of this presentation about the OPIL Logistics Automation Library. Thank you very much for your attention.